Hi. So before we can talk about Linux for the Wii U, we have to talk about Nintendo's original OS for the console, which was called Cafe OS. And there's a lot of interesting things about it, but by far the most interesting part is the dual CPUs that it uses. Inside every Wii U, there are two CPUs. Uh, well, there's actually like 8, but we only care about 2 of them. The first one is the ARM, and the second one is the PowerPC. I don't know why the PowerPC is round today. Now, all of the interesting hardware in the Wii U is connected onto the ARM side. So things like your USB, your Wi-Fi, your storage devices, like the NAND and the USB, obviously, and all of the cryptography and keys related stuff, so like your OTP, for example. On the PowerPC side, we have games, and the games need a GPU, so the GPU is connected over here. So we have 2 CPUs. The ARM side runs its own OS called iOS-U with drivers for all of this stuff. And the PowerPC runs Cafe OS, and it's running the games, it's running the system menu, it's running the internet browser, all the stuff that you're used to. Now, obviously the PowerPC talks to the GPU, the ARM talks to all its stuff, but there's a communication link between them where the PowerPC can request things like, please give me this file for the game, or whatever it is. The reason that Nintendo designed it this way is that, in theory, if anyone were to exploit the games or the web browser, they were worried about the web browser, if anyone were to exploit this, you wouldn't automatically get access to all of the interesting stuff over on this side, because the ARM still arbitrates all of that access that the PowerPC requests. So if the internet browser starts asking, hey, what's the Wii U common key? Can you read that out of the OTP for me? Obviously, the ARM's going to be like, no, the web browser shouldn't have access to that. This design was actually quite effective up until sort of mid-2016, or late 2016, actually, right before the Switch came out. We didn't have any exploits that were able to cross this gap, and so we were stuck with what the PowerPC could do. Okay, so I've kind of simplified the situation a little bit here. We have the iOS-U, which is running on that ARM CPU. It's got all its interesting hardware, like the USB. And over on this side, we have the PowerPC doing whatever it's doing, probably running some game or the system menu or something like this. And we want to take over the iOS-U side because we don't want to be arbitrated. We want to have access to this USB and other things. How can we do that? Well, luckily for us, some of the first CFWs for the Wii U released around 2016 when we got those first exploits that jumped the gap from PowerPC to ARM. They worked by entirely erasing the iOS-U and loading a whole new firmware. So Cafe OS already supports rebooting into a different firmware. It uses it for system updates and for transitioning into Wii mode. That's a virtual Wii mode. So what we would do is we would just redirect that to the SD card and load, like iOS-U star, which has our modifications applied to it. But the point is, it's a complete image. It's like a complete virtual machine, like all the files are there, everything. We've just modified a few of them, right? In order to make this custom iOS-U that's going to have all of our CFW things. Now, custom firmwares have moved on. They no longer completely reload this to replace it with a custom version. They instead just patch the one that's already there, which is a lot faster. But the ability to work with these complete replacements still exists. And the way that works is with the firmware images. So these complete replacements are stored in a file called the firmware image. Fumage. Fumage. We have our firmware image. It contains a custom iOS-U or something, but not really anymore. These are still used today by primarily Minute. You may have heard of Minute if you're a Defuse or an ISFX hacks user. It is a sort of recovery menu system. You can go and you can make a NAND backup, you can change your SATA device type, you can change all this sort of thing. And it works by completely replacing iOS-U. You can't run a game under Minute, you have to boot iOS-U first, because it doesn't speak the right language on the PowerPC side. But you can do a whole bunch of stuff with Minute that you wouldn't normally be able to do under iOS-U, such as raw NAND access, this kind of thing. Now, because Minute is still in regular use, and we have all these legacy CFWs, the ability to load a firmware image has actually remained in all of the current exploits. So Aroma still has this ability, Tiramisu had this ability. It's all still there, which is really convenient. So that brings us to Linux Loader. Linux Loader is a fork of Minute with all of the system recovery stuff stripped out and replaced with, well, some basic Linux loading stuff. Let's get this out of here. So let's talk about Linux. We wanted to take over the ARM in order to run our custom, in order to get access to this USB stuff. But we want Linux to be running on the PowerPC because it's got 3 cores, it's much faster, has access to all of the RAM. The ARM is like 500 megahertz, and it's a really old silicon design. It's like from the late 90s, like it's really quite bad. So we would prefer to run all of the actual meat over here. So that brings us to Linux Load. Linux Loader, which we've loaded in. How do we get from here to here? The PowerPC has been, ever since CafeOS exited, in reset, in stasis. It's frozen, it's kind of off. You can think of it as being off, right? So we're going to activate it back up. So we'll just, Linux Loader has access to everything, USB, SD card, whatever. We just read Linux and we just put Linux over here. And then we just turn it on, right? And then it's just going to run. Well, in theory, but in practice, it's not so simple. Nintendo knew that people would be able to get control of the ARM, especially in virtual Wii mode, where there was a whole bunch of existing exploits from day one. So the PowerPC has a new security feature. It has the boot ROM, so I'll put the boot ROM up here. When you turn on the PowerPC, instead of starting to jump to Linux, it first jumps to the boot ROM. And boot ROM's job is to verify whatever it was going to run. So it does a decryption, and it does, critically for us, a signature check. Only Nintendo can create valid signatures, and they only sign CafeOS stuff. And obviously this is not CafeOS, so it's going to fail that signature check. Now there's a very funny trick to work around this if you have control of the ARM, which we'll talk about. I'll make some more space over here. Alright, and we'll have just our ARM up in the corner here. Okay, so we have the PowerPC. And we want to operate Linux, but it's not going to work that way because it will refuse to start if it's not a Nintendo signed thing. So what we do in the ARM, we load the original Cafe kernel. Now this is Nintendo's code, they signed it, so the PowerPC will have no problem with this. Obviously we don't want it to actually run that because we're trying to run Linux. The PowerPC will start chewing on this binary, it will verify it critically. So it verifies it, and then it ticks off and it says, this is good. Now it's also encrypted, so it starts, rearranging the letters to try and decrypt it, get it in the right order, ready to run. And it actually does this in place. So if you imagine there's a whole bunch of random letters here. Well, whatever. And what it does is it decrypts each of the parts of the binary, it rubs it out, remember it's still remembering that tick there, and it replaces it with the code. And then it just slowly works its way down the list. Right, so we can imagine the PowerPC is currently in progress of decrypting. So it's up to here. Now what's interesting is that while all of this is going on, we still have control over the ARM and we can still run whatever we want up here. And remember, we can access this memory. We're the ones who put the Cafe OS code here in the first place, right? And the PowerPC is going to remember this tick off. So if we, from the ARM side, just watch for the code to appear, once we see it, we can assume it's down in the bottom half. And we can just override it with Linux. And the PowerPC is still working away down here. You know, maybe it gets down to the next stage. And it's going to reach the end. And it's going to be happy. Because remember, it's remembered that tick from when we had Cafe OS before. It doesn't check a second time after the decryption. So as long as we can kind of be fast enough and get in there while it's still busy and swap out the top part, well, now it's going to boot Linux. Because it sees the tick and it says, yeah, this is all good. I finished my decryption. And it just jumps to the start, which we have overwritten in the meantime. This is a objectively hilarious bug. More of a design flaw, I suppose. This was discovered by Fail Overflow all the way back in 2013, basically immediately after the Wii U was released. They discovered that this was possible. Because they were mucking around in virtual Wii mode, and they had access to the ARM side of things with some old Wii bugs that they were using. And this kind of bug is called a time of check to time of use bug. Because it checks it, remembers the check, and then there's some time before it actually gets used. And we can take advantage of that time by tampering with it while it's doing something else. Something I just want to quickly clarify is that all of this code, as I said, it was discovered back in 2013. All of this code is from Minute. I didn't write any of it for Linux. Just adapted it a little bit. Anyway, so we're in. The PowerPC is now jumping to Linux, and at this point we can kind of pretend the ARM doesn't exist anymore. It's done its job. Okay, so we should just put VM Linux in here and jump to it, right? And then we should be set. It should just start. We should run. Well, kind of. The Linux has certain expectations. It wants a device tree. And this is like a description of the hardware that it's running on. So, you know, if it's running on a Power Mac G4 or a big Talos workstation or a Wii U, it needs a device tree that tells it about that hardware. It also expects a command line. Got an L there. And this is like root equals dev sda1, you know, set some configuration for your graphics card, whatever, you know, kernel command line stuff. It also expects the registers to be a certain way, like R3, R4, R5. This is basically CPU internals. It also expects the memory mapping to be a certain way, which is a whole kettle of fish into itself. And maybe there's an init ramfs, and maybe there's, you know, all this other stuff going on. And traditionally, all of these tasks are going to be done by a bootloader, right? But you might remember something about the way that we are running, which is that up until this point, the only code of mine that has run has been on the ARM. The PowerPC is just Linux, right? So it's running on an entirely separate CPU. It can't meet all of these expectations, especially these last ones about the state of this CPU. It can't reach in and set the registers in the memory management configuration. Thankfully, Linux has a solution to this. It's called the boot wrapper. It was designed for bootloaders that don't know anything about Linux, but it's also very convenient because it meets all of the expectations that Linux has. So we can take advantage of it for our weird dual CPU setup as well. So the way the boot wrapper works is fairly straightforward. This is memory. you know, mem1 address 0 is over here. So we're going to have our boot wrapper loaded in here. And this is a tiny piece of code. You know, maybe 100 kilobytes, tiny little piece of code. And its job is to take a kernel, probably a compressed kernel, and the device tree, and it's just we're gonna jump here, right? PowerPC jumps here, starts executing the boot wrapper. Its job is to uncompress the kernel, it makes a note about where this device tree is, and once it's done, it redirects execution into Linux. So this way, the boot wrapper is able to meet all of Linux's silly expectations. It's able to decompress it if it's a compressed kernel, it's able to find the device tree, it's able to set up the registers, it's able to copy the command line over, does all of this stuff on the actual CPU that cares, and then it can jump in and start executing Linux. And there you go. Linux is now running. It will, you know, override all of this, you know, whatever, and then start, you know, putting, you know, the frame buffer and the drivers and all these other things that make Linux, right? The stuff that we actually care about. And so that is how you can take a Wii U from running Nintendo's Cafe OS software and get it running Linux entirely on the PowerPC with no overhead, no emulation, no anything like this. I have a quick bonus round. So, you know, we're running Linux. Yay. What happens with ARM up here? Remember it had like the USB and stuff? I never came back to that. There's still a big dividing line. Linux can't see the USB. Wasn't that the whole point of Linux Loader? Well, there's a very funny feature. It was originally on the Wii, and it was carried over to the Wii U. And we have no idea why, because it doesn't make any sense for Nintendo's security model, and it kind of destroys it. Remember, the whole point of having a second CPU is that it can protect the sensitive stuff. I mean, this is not particularly sensitive, but some of these other things are, right? Protects the sensitive stuff. So if we have any weird things running over here, I mean, this is a weird thing, right? It's not going to access it. But like many great hardware ideas, they left themselves an out if they ever decided they needed it. And that out is called AHB prot. P-R-O-T. AHB prot. AHB prot, maybe. And if you poke this, you write 1 to the register, suddenly this line melts away. And Linux can just reach out and touch whatever it needs. And I mean whatever it needs. This is why there's an OTP driver in linux-wiiu right now. And so this is great. Basically, at this point, Linux Loader's job is to get the hell out of the way. It copies itself into a secluded corner of RAM and then just does practically nothing. There is a debugging console if you want it, but it's not going to touch any of this hardware, and that's what we care about, because then Linux can touch it, and it's not going to have its toes stepped on. So yeah, there's a little bonus round, a very funny security feature. Just jumping in during editing, I made a factual error here. The AHB prot register was discovered by Ben Bushing-Beyer in 2009. He was a major pillar of the Wii scene and made many great discoveries and many great blog posts, including one about this AHB prot bug, which is very cool. And it was a big boon for the GameCube Linux people, and we are still benefiting from it on the Wii U as well, which I find fun. Well, so this was kind of a test of doing more of a tech explanation, kind of lecture situation. Let me know what you think. Let me know if this format works. Let me know if I'm too rambly. And maybe I'll do more of it, because there's a lot of stuff to talk about that is not very well documented, and writing it down takes 100 years. So, you know, maybe I get my pencils out and go to work more often. But yeah, let me know what you think. I will be around.